And the topic in this section is called transverse waves. All right, so I don't know what it is, but from my point of view, there's something about a wave that's just really fascinating and really interesting. And I think what it is that, and I think you have some sort of idea what a wave is, and we're going to talk a lot about it exactly here and draw pictures and everything else. But just from a big picture point of view, I think you know a wave is just some sort of disturbance that propagates and that travels somewhere. And that disturbance or that propagation can carry energy with it. In other words, if you're standing on the beach, or let's say you're standing in the water at the beach, and the waves come crashing in, you know that when those waves hit you, they have carried energy because they can knock you over. They can actually tumble you over. So they started out hundreds of miles away at sea, and somehow through that disturbance through the water, they've come and they've knocked you over. Same thing with taking a sunbathing at the beach, right? So you're sitting at the beach, you're not doing anything other than laying down. The sun's waves, electromagnetic waves in those cases, which is just a disturbance in the electromagnetic fields that travel from the sun to the earth, those waves come all the way through space, 93 million miles away, and then come through our atmosphere, come right down on top of you on that beach. And they carry energy with them. The reason that you know they carry energy with them is because you get hot, right? Obviously, they carry heat, that's energy, and they eventually burn you. They actually carry enough energy all the way from the sun that they burn you. Now, that's just pretty fascinating to me that you can have a disturbance carry that energy like that. So that's why I think waves are interesting. What we're going to do in this section is cover transverse waves. We'll talk what that means in just a second, but as we go forward, I want you to understand that this section and the subsequent sections are absolutely critical for those of you going on into Physics 3, which I'll cover in a subsequent course, and also into those of you that are studying electrical engineering and physics and all of those subjects where wave theory is really, really important. So this is the bedrock. This is the bedrock. So what is a wave? We've already talked about it, but I want to write it down because it's very, very important. So a wave, in general, is what? It's a disturbance in a medium that carries energy away from the source, which is exactly what I said. Now, to give you an idea of what this means, if you're in the water, the source would be, if my hand is here and I'm wiggling the water up and down, well, that's the source. I'm putting energy into the water, and those waves carry the energy away, and they'll just go on and on forever, getting less and less intense as they spread out. So what are some examples here? Obviously, you have sound waves, which travel through a medium. See, they're a disturbance in a medium. Sound waves travel through what? Air, usually. But of course, if you're swimming in a swimming pool and you put your head underwater, you can still kind of hear what's going on. It doesn't sound normal, but you can hear. So sound waves can obviously propagate in water as well. But usually when we talk about sound waves, we're always talking about air. We can talk about water waves, which are the waves at the beach. And of course, they propagate through water as the medium. Just another example, a wave on a string. Wave on a string, obviously the medium would be the string. In parentheses here, I'm trying to tell you what they're traveling on. And finally, I'm going to give a little honorable mention here, a light wave. Also known as an electromagnetic wave. That's the more intimidating way to say it, but really it's just a light wave. What medium does light travel through? Well, it turns out, and this is getting into some more advanced physics, this is an exception to this little definition here because it requires no medium. Now, we're not going to talk that much about light waves in specific here. I mean, all of the theory we're going to talk about in terms of how to write a wave down, it's going to apply to electromagnetic waves, which are light waves. But there's one huge difference between light waves and the rest of these that we're going to talk about, and that is that light doesn't require a medium. Think about it. You flick a wave on a string, you require the string to carry the wave. You disturb the water is required to move that wave forward because that's what the wave is in, right? If you're speaking from me to you, the sound waves are going out through the air, through the molecular collisions reaching from me to you. The medium is the air. And for a long, long time, hundreds of years, every scientist in the world, a few hundred years ago, also thought that light required a medium just like everything else. But it turns out through lots of experimentation and theories and so on that light doesn't actually require any medium at all. And that is how the sunlight can go from the sun to the earth through dead empty space. You can suck every molecule of air out of space in a jar or whatever, and the light will sail right on through it. So I want you to think about that because it's not intuitive. It's not something that you would say, oh yeah, light doesn't need a medium. It's very, very odd. Light is very, very special. It's all around us. We take it for granted, but light is very, very special. So keep that in the back of your mind. Now, in general, there are two types of waves, two broad classifications of waves. The first one we're going to talk about, I'll give you the definition, but we're really going to cover that in detail in a subsequent section. The second type of wave we'll cover in great detail. First type of wave is called a longitudinal wave. A longitudinal wave. Second type is called transverse wave. Obviously, transverse wave is what we're going to cover in detail in this section. Let's talk about longitudinal wave briefly, just so you know that it exists. Longitudinal wave. Look how this is spelled. Longitudinal. Longitudinal wave. All right, it's a wave where the medium, which would be, water, air, or whatever, the medium oscillates back and forth in the direction, DIR's direction, in the direction of wave travel. And you can guess by the fact that I'm laying it out like this that a transverse wave, which is the topic of this section really, does not oscillate back and forth in the direction of travel. Now, what does this mean? This is a complicated looking definition. You need to think of a spring or a slinky. So for those of you that have played slinkies when you're a kid, you'll understand what a longitudinal wave is very easily. So here's a slinky. It's a spring like this. All right, that's a slinky. Now you have to think and use your imagination with me here because I do not have a slinky as a prop. But if you were to take this slinky and shake it, not up and down, forget about that, forget about up and down. That's transverse wave. We'll talk about that in a minute. But let's say you give it a little tap in this direction, like this. Well, if you can remember back to your slinky days, and to your spring days, if you give it a quick little flick, it's going to compress the spring, and that compression is going to sort of travel down the end. To the end. Eventually it'll hit the end, it'll bounce back probably, but it's going to basically go in this direction. So you can see the medium, which is the slinky in this case, oscillates back and forth in the direction of wave travel. In the direction the wave's going this way or the wave's going this way, but the oscillations are occurring like this. In other words, they're not going up and down like a transverse wave we'll talk about in a second. They're going in the direction of motion. That's basically what a longitudinal wave is. And the main kind of longitudinal wave is the sound wave. That's the main kind of longitudinal waves that you'll concern yourself with. Several sections here in the future we're going to talk in detail about sound waves, calculation of sound waves and things like that. But just for in the back of your head, remember that a longitudinal wave is when the oscillations go in the direction of motion like this, and generally sound waves is the biggest kind of longitudinal wave there is. When you think about it, when I'm speaking, my voice is going out to you from your television or your computer. What's happening is my vocal cords are vibrating. Or in your case, you're watching a TV, your speakers are vibrating in there, and that's creating a oscillation in the air that's around those speakers. And it's pushing, literally, if you turn up the volume of a really big speaker, you can see it moving back and forth, coming in and out like this. And it's pushing the air molecules back and forth. So what's happening is you're creating an oscillation, a back and forth movement of the air. And that propagation, since you have millions of air molecules between me and you, that oscillation is propagating from me to you like this. That's why it's a longitudinal wave. Think about long, meaning it's oscillating in the long direction, long way from me to you, meaning longitudinal. So longitudinal means oscillating those elements back and forth like that. It's just like the slinky. In the case of a sound wave, the slinky is kind of like the air molecules that are very close together and have, attraction and repulsion, electrostatic attraction and repulsion between them, but basically they're bouncing off each other, and they're doing that in the direction of me to you. They're not going up and down like a water wave would. That's a longitudinal wave. Put it in the back of your head. We're going to learn about it a little bit later in detail in a few sections. Now, what I want to focus a little more time on is called transverse wave. For a couple of reasons. Number one, I'm an electrical engineer, so I'm much more interested in electromagnetic waves, which are light waves that come from the sun or any other galaxy or anything out in space that has light, or X-rays or microwaves or infrared or anything like that. Those are all electromagnetic waves, and those are all transverse waves. So my natural interest is in those kinds of waves there. Most of the waves that you'll find in nature are transverse anyway. Like we said here, the water waves, waves on a string, etc. So if we had to write a definition, it would be a wave where the medium, which would be like the water or the string or whatever, the medium, oscillates back and forth in the direction, DIR's direction, perpendicular, that's what this symbol means, perpendicular to the direction of wave travel. All right, a wave where the medium oscillates back and forth in a direction perpendicular to the direction of wave travel. What that means is if you have a wave going down like this, think about a wave on a beach or in the ocean, that wave is going this way. The water itself is going up and down, and you can kind of see that if you look in a bathtub or in a fish tank or aquarium or something like that. You'll see the wave, the crest of it, propagating like this, but if you look really closely at the water itself, you'll see the water is rising and falling as the wave passes by. Water is going up and down. In other words, the water is oscillating in a direction perpendicular to the direction that wave is going. That means it's oscillating up and down as the wave is going that way. And I do briefly want to show you what that looks like. I think you all have an idea, but so this is just a jump rope, and a transverse wave would be if the medium was this rope, the medium of wave travel was this rope. If I give it a little flick on the end over here, you'll see that the wave will propagate down to the other end. So the crest is traveling from this direction to this direction, but if you look really closely at the jump rope itself, each little point of the jump rope just moves up and down. So if you were to fix your gaze right here on one section of the jump rope, you would see, if I were to slow it down, you would see that that jump rope would be going up and then down like this. It would be going up and then down. But because all of the atoms and molecules are really tightly bound in this jump rope, and they're basically connected for all practical purposes, when one of them moves up and down, it kind of causes the next one over to move up and down, and it causes the next one over to go up and down, and it causes the next one over to go up and down. So it's kind of cool when you think about it that just going up and down causes a disturbance to move from left to right, which is perpendicular to this up and down that you have here. Notice it's bouncing off the end here and coming back the other way. We'll talk about that a little bit later too. So I would like to draw a picture of a transverse wave because I think it will be very, very enlightening for you here. So here's a simple little graph, okay? And let's say that this is distance x, and let's say this is the distance of the height of the wave y. Now let's just say for giggles here that the wave starts out like this. It's a sinusoidal wave. You're going to find, by the way, all of these waves in physics are sinusoidal. That's why sine, cosine, and all those trigonometric functions are so important, because in nature, sine waves are everywhere. Real life waves are always sine waves. And if you ever see a wave that doesn't look quite like a sine wave, you can always write it mathematically as a series of sine waves. So I'm just telling you this because sine and cosine, which is really the same thing, the same shape, they're very, very important in nature. So if you have any kind of hesitation on using sine or cosine or know what that looks like, please go back and review it, because it's essential. So this is a simple sine wave, and you can sort of imagine that this is a string, just like we were talking about. It's going up and it's going down like this. Now this is its extent in the distance direction. So if I had the string, it would be looking like this. But of course, this hasn't actually traveled anywhere. It hasn't moved. But let's say I let my stopwatch go a few seconds, And a few seconds later, let's say this wave travels like this. So it's a little bit farther down the way. It's very, very important that you understand this. This is a distance in x. This is meters here, okay? And this is meters. So this is the height of that string, and this is the shape of that string. Just if you were to take that video and pause it a few minutes ago, as I started the wave, if you pause it, it would have a shape like this. And then if you unpause it, pause it again a few seconds later, that crest would have moved a little distance to the right. And that distance that it moved means that that wave as an element has propagated. So even though up and down, the elements have only moved up and down like we talked about in the string, it's actually sending energy this direction. So the wave has really moved. This distance from this dot here, from this point here to this point here, the entire wave, the entire extent of it has moved. It's exactly what happens in the water. When you see a wave like this, individually the water is going up and down, but the wave itself has propagated off to the left or to the right, off to the shore. All right, so what you're going to look at here, this would be time t, let's say for this point, and this right here would be a time t plus delta t. In other words, sometime later. Delta t just means change in time. So if I start my stopwatch and then stop it, a certain time has elapsed, delta t, and then the entire wave has moved, right? And so this is the wave's speed. So a lot of times you want to know what speed the wave has actually traveled at. So the way you would do that is you would look at a point on the wave, and then you would let your stopwatch go, see how far it moved, stop your stopwatch, and then calculate the speed, distance over time, just like you did in Physics 1. One thing I want to say before going forward is this definition of a transverse wave, medium oscillates back and forth in a direction perpendicular to the wave travel. That is true for water waves and string waves and some of these other things we've been talking about. But for light, which I told you special, light does not require a medium to travel at all. So what's oscillating in a light wave is simply the electric and the magnetic field that we'll talk about in Physics 3 that's oscillating back and forth. But it doesn't require something else, some other material to actually be in. The electric and magnetic field is oscillating, and that's what's actually causing the energy to be propagating forward. So the medium here, when I'm talking about medium, I really want you to think more about water waves and string waves, because that's really where that idea of a medium really makes more sense. You talk about light waves and things get a little more muddy because light waves are very special. Now I want to give you a little bit of an aside real quick. I want to continue our discussion. We've shown you what a wave really looks like. We've said that they can propagate, they can send energy that way. But mathematically, what is the equation of a wave? This is the central topic of the entire section. What is an equation of a wave? Well, in general, this is what it's going to look like. And I'll explain all this in a second. Y is a function of position and time is going to equal some maximum y times the sine of kx minus omega t. Now don't worry too much here. I know this looks like a lot of foreign material, and it does, and it is, but you'll understand it all here in just a second. Y is simply how far up and down your thing has oscillated. That's why it's labeled y right here. So what you basically have an equation for is the distance above or below the axis there as a function of position and of time. And the number out front here, y sub m, is the maximum value of y. It's the same thing as the amplitude in the previous section. Some books might even have an a here. It's okay. It's a number. Ym, maximum amplitude, a is an amplitude. It's the same thing, but in real life, when you actually write it down, you're going to have a number out here in front of your sine, and then you're going to have sine kx minus omega t. Now let me go one by one. Omega, which is the angular frequency. You learned about that a few sections ago. We talked about oscillations. So that material should be fresh in your head. It's the angular frequency of the motion. T is the time that's elapsed in seconds, because you know that this wave is going to look different at a different time because it's propagating, right? X is how it basically deals with how this wave looks in space. In other words, what does its shape look like? Does it look like this? Is it really stretched out like this? What does that mean? So X is basically that, and K is, we'll talk a lot more about K in a second, but it's basically called a wave number, and it's just a number. This is a number just like the frequency is a number. It's a number that goes in and it describes that shape of the wave. Basically, it's going to tell you how stretched out or how compressed that thing is. So it's really important that you understand what this is. I could easily just tell you, hey, this is what a wave looks like. Write it down, go on with your life. But I really want you to understand what it's doing because it will make it easier. Okay, so I want to write a few things down. This is the max amplitude of the wave. It's the maximum. This is called the amplitude, just like before we talked about the amplitude of an oscillation. This is the amplitude, this distance between here and here. So that's y sub m, maximum amplitude, maximum distance above the value. So let me put max value of the wave, which we also call the amplitude. Okay. Now this stuff here, these things right here that have involve time. Basically, if I want you to just sort of pull one thing away with it, this deals, I'm going to write it just like in English, this deals with the oscillation with respect, that's what with respect to, WRT, with respect to time. So this stuff involving t, this involves the oscillation with respect to time. And then this stuff involving k and x, this deals with the spatial shape. All right, so I want to stop here and really make this, just drill this in. All right, you know from conceptually talking about it that wave involves something about time, because you know that as you click your stopwatch, the wave propagates, so it has to be a function of time. You also know that it has to be a function of space, because as this is a graph of space, right? This is a graph of space in this direction and space in this direction. We've shown that the wave has propagated. But if you look at a different point in space, the wave has a different value. Here it's much higher. This might be 5 meters. Here it might be -3 meters. Here it might be +3 meters. Here it might be 5 meters again. Here's 0. So as I go in space, in other words, if you look at that jump rope and pause the video and you have that crest there, well, as you look in space, different values of x, the value of that wave is going to be different, just like any sine wave that you draw on your graph. So the equation of a wave, the reason that it works to describe a traveling wave is because the equation itself inside of the sine argument has something to do with space, which describes the shape of that wave at any instant in time, and it also has a propagating function that talks about how the oscillation oscillates with time. In other words, you click your stopwatch, and at this particular point, it's going to go up and down, up and down, up and down, or at this point, it's going to go up and down, up and down, up and down, and that's what this is describing. So in the previous sections, when we're talking about oscillations, we didn't have this at all. We only had sine of omega t, because in those sections, we were just looking at an oscillation in one point, up and down, up and down, up and down. It only involved time. Now, it's not, it's larger than that. We've expanded it so that we have an entire wave shape, right, that's moving off to one direction. So as time goes on, every one of those points is oscillating up and down. That's why you have the time dependence. And the entire wave is moving, so that's a time dependence. But at any given time, if you pause your video, let's say, you have a shape here, and that's what this is describing here. So I think that's enough talking about that. We'll get into a lot more examples and really showing you how it works in a minute, but that's why every wave that you see has to have something involving x and something involving time. If it only has x, it's not a wave. If it only involves time, it's not a wave. You have to have something involving x and you have to have something involving time, because a wave by definition involves space and time. So you might read a book and it might have a fancy definition. A wave is something that travels and involves space and time. It sounds so mystical. It's not mystical. It's just that time goes on, the thing has to travel. It's a function of time. Pause your video, and one instant of time, your shape is going to be described by this x, this extent that you have in x. So that's what it is there. All right. So what I want to do is tell you one more quick thing before we really get into more detail. I want to give you a little bit of an aside. Now, in some books, your waves might be written as sines, And in some books, your waves might be written as cosines. So some of you may have been looking up to now, and your book might have something involving a sine, and you're on the same page with me. Some of you might be using a totally different book, and it might have something involving a cosine. And you might be scratching your head saying, why is this guy telling me the wrong thing? Waves are obviously cosines, not sines. It's, the case is that the sine and the cosine really are exactly the same shape, but just one of them is shifted from the other. So you can write a wave in terms of sine or cosine, and it's really describing exactly the same thing. So if your book has a cosine here, then you just use the cosine and that's fine, but it's describing the same kind of thing. And I want to show you briefly how that's the case, because if you think back to your trig, which is really what I'm going to ask you to do here, if you think back to your trig, this would be pi over 2, this would be pi, this would be 3 pi over 2, and this would be 2 pi. So this is one complete revolution around the unit circle. So the typical sine function, which is sort of what I've drawn up above, is going to go up at a maximum of pi over 2, down through pi, negative maximum here, and complete the circuit at 2 pi. That is one cycle of a sine. Sine always starts from the origin. Okay? Now if we were to draw a cosine on the same graph, it would start over here at a maximum of 1, and it would go down through pi over 2, it would reach a maximum at pi, it would come up through 3 pi over 2, and it would reach a maximum here. So you can see this one has completed one full cycle as well. But if you look at the shape of them, they're exactly the same shape. And I think you all know this. But in other words, if you kind of think about it, we started the graph here, but I could kind of dot this over here. This helps me a lot. If I continue to dot it here, then you can kind of see that this, let me label it for you. This is the sine, and this is the cosine, the purple. So you can see that the cosine is simply a shifted version of the sine, or looking at it differently, the sine that we've been talking about is simply the cosine shifted a little bit. But the shape is what's important. The shape is the same. So some books might have sines and some books might have cosines, but they're exactly the same. And just to go just a little bit farther with you, the sine of some number is just equal to the cosine of that number minus pi over 2. Now, if you remember back from algebra, you looked at shifted functions. That may seem like ancient history to a lot of you guys, but if you look back in your algebra that you studied a long time ago, you can shift a function by just taking its argument and subtracting a number from it inside the argument. So if I wanted to shift the cosine, I would simply take the argument, which is x, and I would shift it to the right by subtracting pi over 2. So if I look over here and take this cosine function, and I want to shift it to the right, which by pi over 2, which is what I want to do to move it over here, this is a shift of pi over 2. I would simply subtract pi over 2 on the inside. So the only reason I'm telling you this is just to prove it to you, to make it absolutely crystal clear that if you have a wave in terms of sine of x, you can write that wave in terms of cosine, but you might have like an extra term hanging out here if you were going to make them exactly equivalent. But the most important thing I'm trying to get here is that the shape of these two things are the same. So that's an aside. If you have in your book cosine here, don't fret it. Everything is going to be exactly the same as what I'm teaching you here, except that you'll hit the cosine button on your calculator instead of the sine button on the calculator, but they're describing the same thing. When you're propagating a wave, you can describe it in terms of sine or a cosine because the shapes are exactly the same. Okay, the next step on our journey to understanding traveling waves and the way that we've written them is to understand how that equation that I just wrote a minute ago that describes a wave, how exactly does it describe this traveling wave? I want to go into more detail so you really understand it. I already told you it has a spatial extent in x, and I already told you it has a temporal or a time extent in time. Together they somehow describe the traveling wave, but I want to go into detail on that. So how does it represent a traveling wave? Remember that we just said that a wave is a function of space and time, and it's just the amplitude of the wave, ym, times the sine of kx minus omega t. You might as well memorize that. Kx minus omega t, kx minus omega t. That's going to be inside of the sine. The best way to do this, or I think the best way to do this, is to look at two different cases. The first case we want to look at The first case that we want to look at is at time equals 0. In other words, a snapshot in time. You pause your DVD, a snapshot in time, and you see what you have. So if we were to put time equals 0 in here, then what we would have is that y as a function of x at time equals 0, that's why I put a 0 here, time equals 0, is equal to the amplitude of the wave times the sine of kx, because time is 0. So I'm actually pausing the video right when the wave gets started, t equals 0, and what I have is an amplitude times sine of kx. And if you were to graph that, you would just be left with a sine. It would go up, and it would go down, and it would go back up, and it would continue on and on. But this is a function of x, and this is obviously the amplitude there, or the distance above the rest value, y. So as you pause the video, you're given a spatial extent right there as you go. Now, let's go on to the second case. Now we've looked at the spatial extent by just taking a snapshot in time. Now what about when x is equal to 0? Let's look at how it behaves in time. So the wave will be a function of space and time, but we've said we're looking only at x is equal to 0, so it's only a function of t, function of time. Now we're going to say that that's the amplitude times the sine of negative omega t. Because if you look, it's kx minus omega t, but I'm saying, okay, I'm looking at x is equal to 0. I want to see how this thing behaves in time only. So I put x is equal to 0, and I'm left with this simpler equation that I know how to graph, like this. Now the first thing I want to show you is that this equation has nothing to do with x. So really this is just like the first sections of the course here. This is just an oscillation of, back and forth oscillation. So if I really wanted to get picky about it, then all I'm doing here at x is equal to 0, which is right here where my wave started. If I only look at this point, I don't look anything else in terms of x. I only look at this point, start my stopwatch and watch it. I'm going to see that it's going to go up and down like this as time goes on, up and down, up and down, up and down, because it's a sine as a function of time. So at this point, it's going to go up to a maximum of ym, and it's going to go down to a maximum of negative ym, and it's going to keep doing that over and over again, right? It's going to keep doing that over and over again. So if I wanted to draw a graph in time of that, just like we were doing a few sections ago, then I would label this time, and I would label this y, and then I would see that at x is equal to 0, it would be going up like a sine and down like a sine again. So why am I telling you all this stuff? I'm really just trying to show you that if you freeze time and only look at how it behaves in space, you're going to get a sine wave in space. That's the shape of the string, like this. Now freeze that in your head for a second. If you only look at one point on the string, which is at x is equal to 0 here, but it could be x equal to anything, but I pick x equal to 0 and I only look at that part of the string. And then I watch it in time, that part is going to go up and down, just like we talked about the water waves doing that. And of course I can stretch that out in time, and I can see that it's going to look like a sine because of what I really have here. So you can see that this function, kx minus omega t, has a sinusoidal dependence in space and a sinusoidal dependence in time. So it has a spatial shape, okay, and it has an oscillation. And so putting those two things together, that wave is going to travel off to the right because, as I said, if I were to look at the next snapshot in time, it would look like this. As this thing oscillates up and down, it's going to cause that wave to move off to the right. And so that's what's going to happen. Just like the jump rope. You flick the jump rope, I'm only moving my hand up and down on one end. That's what this is really trying to tell you. At one point on the string, it's only moving up and down, but because it's connected in a string, causes the adjacent elements to move up and down, which causes that guy to propagate to the right. So just reiterating, a wave has to have kx minus omega t. Now, I haven't told you what k is at all. It's a constant. We'll talk about it in a second. But you have to have spatial dependence and time dependence. So memorize this. This is the equation of a wave. It looks like this for water waves. It looks like this for electromagnetic waves, even though we won't talk about those until the next course. Only these two things together describe a traveling wave. All right, so what do I want to do? Let me erase this real quick because I'm going to reuse this little graph. And let me go ahead and erase the dotted lines here, because I'm going to reuse this. All right. Now at t is equal to 0, time is equal to 0, I pause the video and I have a shape that my string has described across the screen. Notice that obviously if I had a longer jump rope, it would continue to go up and down, forever like this, or as long as my jump rope is. Notice that it repeats, just like you would expect it to. So from here to here, it basically repeats. So looking at this distance, from here to where the thing repeats, this is called a wavelength. And it's called a wavelength because here's your wave and here's the length of it, the length between one repetition. All right, it's basically exactly like what we talked about before when we talked about the period of an oscillation. That's how long it takes to repeat. This is how long in space it takes something to repeat. So let me just define it. The wavelength is the distance where the wave repeats. So nothing too surprising. Now, how do we calculate that, or how do we relate this? Let's think about this for a second. The sine function repeats, itself when the inside of the sine function, which is kx, increases by 2 pi. And that happens after one wavelength. Okay? In other words, this equation is describing the shape of this spatial wave shape here. And we know that this distance in meters that it takes between here and here for it to repeat is called the wavelength. But this equation that we have that describes a wave, the sine function itself is cyclical and it repeats when the argument increases by 2 pi, which also happens after one wavelength of distance there. If you plot this in your graphing calculator, you'll see that it goes up and down. The distance between the crests is called the wavelength. So if we were going to take advantage of that, we would just say the inside here, kx on the inside is equal to 2 pi. In other words, the inside of the sine function has to increase by 2 pi for that thing to repeat. And we saw for k, what you'll get is k is equal to 2 pi over x. But in this case, we've said that we've repeated, so it's actually lambda. Okay, a more clear way to say that would be that k times lambda, k times one cycle of this wave is equal to increasing the argument by 2 pi. Basically, this is just an equation that talks about when the thing starts over again. So kx is equal to 2 pi, but whenever the thing repeats, we've gone one wavelength. So I put the symbol lambda in there, solve for k. What you're going to get is this very, very important thing called the angular wave number. All right. In other words, I think you all have a good idea what wavelength means. At least I did when I started learning this stuff. But I really had no idea what k meant. Why would they invent something else called k? Well, the reason is because in the laboratory, you can measure wavelength. I mean, you can actually take that string, flick it, take a snapshot, and measure the wavelength. But you can't just stick wavelength in here because you're taking the sine of something, and whatever you take the sine of has to be an angle. It has to be in radians or degrees, but usually you're dealing with radians. So if you have a wavelength, lambda, that you've measured in meters, you have to convert it to something that you can then dump into this guy. So this is basically, this angular wave number is basically like a conversion factor that converts between meters of wavelength to radians so that you can take the thing there. Because if you look at the units, 2 pi is radians, so the unit of the wave number is radians over meters. So what you've done is you've created a conversion factor, radians per meter. When you put it back in here, times whatever distance you're looking at in your equation, you're going to get radians. So, and I'm really just telling you all of this so that you don't get too wrapped around the axle here. This is nothing more than allowing you to take the wavelength that you have, like a problem on your test might say, a wavelength of a wave is 5 meters, and you're trying to write the equation of a wave. Well, you're going to have to stick it in here to get the wave number because the equation of a wave always talks about wave number. Because of the way the units work, you have to be taking the sine of a radian measure, so you can't just stick meters in there. and multiply it by this, it's just not going to work. You have to define the wave number. So wave number is nothing more than a way to convert this wavelength to something usable. So remember it. One of those things, just like I taught you to remember, that omega was 2 pi f a few sections ago. Omega was 2 pi f, omega was 2 pi f. You had to remember that. I want you to remember that the wave number k is 2 pi over lambda. 2 pi over lambda, 2 pi over lambda, 2 pi over lambda. Angular wave number, 2 pi over lambda. You have to remember that. It's going to come up over and over again in all of your courses for those of you going into Physics 3 and all of the other things beyond it. Wave number is here to stay. You're going to have to remember the wave number. You just take your wavelength, you dump it in here, you get a wave number, and this number is what you use in your equation of a wave. All right, so we talked about that, and briefly I want to refresh your memory. That's why I'm going to put recall from a few sections ago, because you're going to use these in your problem. Remember, I told you to remember, omega is 2 pi f. This is just stuff I'm telling you, I'm writing down just so you can remember it. The frequency is 1 over the period, same as before with the oscillations. So we can say that omega is 2 pi f, but f is 1 over t. So we can say this is omega is 2 pi over t. And we can say that the frequency is 1 over the period. So when we take frequency 1 over the period and we put this in here, then we'll get omega over 2 pi. Just simply taking the period here, the period is 2 pi over omega, take it, stick it in here, and it comes out to omega over 2 pi. I'm just writing a few relations down that are going to be useful as you work on your homework problem. So the new one is the wave number k is 2 pi over lambda. But you've already known omega is 2 pi f, angular frequency, 2 pi times the regular frequency. Frequency is 1 over the period, and you can use these two to derive these down here. So these are nothing new, these are just taking these and deriving it there. So what I want to do next is talk about how we calculate the speed of a wave, and then once we do that, we'll be ready to solve our problems. Okay, now what we're going to do is do something very important. We're going to calculate the speed of a wave. We're going to derive the speed of a wave, and you'll use that frequently in your problems. It's one of the most important equations we have. The speed of a wave. The speed of a wave. How do we calculate it? Well, let's draw a picture first because pictures are good. We're going to continue drawing these until you get it. So here's x, here's the y, which is the height there. And of course, we all know that the wave begins like this and goes like this. And of course, you can keep it going, forever and ever, as far as you want. Now that's at one instant in time, but let's say a few seconds go by and that wave propagates, so it goes to something like this. Not the best artist, but you get the point. So some time goes by and the wave has literally moved over to the right because it's the ripple effect has really caused that. So what we're going to do is we're going to look at two adjacent equivalent points. That would be the crest here. You could look at this point and this point, or this point and this point. It doesn't matter because everything is shifted an equal amount, but we're going to look at the maximum there. And we're going to say that it has moved a distance delta x in a certain time, right? And so this speed at which it has moved is what we call the velocity. So some time has elapsed. Every point on the wave has shifted delta x over, and of course, distance over time is what we define to be velocity. So velocity is distance over time. That's all we're doing, measuring the distance over the time. And if you're taking calculus, that is just rewritten or written equivalently as the change in x, derivative of x with respect to time. If you're not in calculus, don't worry too much about it. It's not going to be that critical. But if you are, it's really useful just to know that we're not doing anything more than dx dt, which is change in x, how much it moves in x compared to how much it moves in time. Okay? So, recalling that the equation that we are using here for a wave is maximum value times the sine of kx minus omega t. So if I'm really trying to say that this wave moves to the right and that every point moves an equivalent amount, then what I'm basically saying is if I want to actually calculate the velocity, I'm going to look and focus at one point and watch that one point move to the next equivalent point, and then I'll know how far it's moved. That is exactly the same thing as taking the argument of this sine, which is kx minus omega t, and just saying it's equal to a constant. Because if you think about it, you put a value of x in here and you put a value of time in here and you do all the calculations, you're going to get a number at this point in x, at this point in time, the value is right here. That's what you're doing. Now, if you're saying that that point has then moved a little bit to the right, you're saying that this argument here is just simply a constant. Another way of saying that is, as time goes on, yes, the thing has moved to the right, but the distance from the axis should be exactly the same, which is what you're saying here. This is a constant, so even though time has increased and I'm looking at a different place in space, the inside of here is remaining to be a constant. So when I take a sine and do all the other multiplications, I'm going to get exactly the same value down here below the axis, or wherever point I'm looking at, I'm going to get exactly the same value. So as those time and space increase, that point remains exactly the same distance, so I'm tracking that point moving. It's very important that you understand that. You take the argument to be a constant, you're simply looking at that point as it moves over exactly to the same spot. So I say it's equal to a constant. Now, this is where we get into a little bit of calculus. We can do anything we want. We can take, just like in algebra, you can subtract something from both sides. We can take the derivative with respect to time of both sides. If you're not in calculus, don't worry too much about this. We'll get to the end and then you'll recognize the answer, and that'll be that. We can take the derivative of both sides, so let's do that. So we will switch back to black. dt of the left side, kx minus omega t. And on the right, we'll take the derivative with respect to time of a constant. Okay, on the left, you're taking the derivative of this and the derivative of this. So what you're going to have here, because k is a constant, it's just going to be k times dx dt, because this is just simply a constant, minus omega is also a constant, so it's dt dt. And then on the other side, the derivative of any constant is just simply 0. So make sure you understand that. K is a constant, so it comes out of the derivative. Take the derivative of x with respect to time. Omega is a constant, pull it out, dt dt. Now, this dt dt is just 1. The change in time with respect to time, there's nothing changing there. It's time with respect to time, so it's just simply 1. So what you're really going to have is k times dx dt minus omega is equal to 0. And so if you're going to solve for dx dt, which is what we're going to do, move omega over, so you'll have omega over k. This is a very important result because notice from above, way up above, we said the velocity of the wave is derivative of x with respect to time. Look at what we solved for. Derivative of x with respect to time. And we found that it's exactly equivalent to omega over k. So if you know the angular frequency in radians per second and you know what the wave number is, then you just divide them and you get meters per second of that wave. Because this is what it's talking about, meters per second. Now, we can do a little bit of simplification here to arrive at a really cool result. We know dx dt is omega over k. We also know, so I'll say recall, that omega is equal to 2 pi f. Okay? And also recall that k is equal to 2 pi over lambda, which we just solved for just a minute ago. With these two things here, we can just go ahead and continue on here. We can say that the velocity of the wave, which is dx dt, we know it's equal to omega over k. We know that omega is 2 pi f. We know that k is 2 pi over lambda. Right? So we just plug in what we know for omega and k. 2 pi is going to cancel with 2 pi. And since this is like 1 over lambda, we can flip it over. And so what you'll have is f lambda. Very, very important result. So what I'm going to do is I'm going to say the velocity of a wave, that's what this means right here, v, velocity of the wave, is equal to omega over k, which we already calculated, which is exactly equivalent to its frequency f times its wavelength. Very, 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 very important result. Most of the time you're going to be using this because in the laboratory you can very easily measure how many hertz an oscillation is, how many oscillations per second that thing is. That's what F is. And you can easily measure with a ruler the distance, the wavelength is between the crest of that wave. You'll get a length in meters. You multiply the two things. If this is in hertz and this is in meters, you will get meters per second. Of course, you could do it with angular frequency and angular wave number. It's exactly okay to do that. In some of your problems, you may have to do it. Most of the time, you'll be using this. And this formula works for, these water waves we're talking about, waves on a string. It also works for light waves. We're not going to do any problems relating to light waves in this section because it's more advanced. But if you know the speed of the wave, which you all know, the speed of light, you've at least heard of the speed of light, so you know what the speed of light is, and you know the frequency of that wave, then you can always calculate the wavelength, and vice versa. If you know any two of these variables, you can always find the third. So if you're operating a microwave oven at 2.4 gigahertz, which is 2.4 times 10 to the 9 hertz, you know the frequency, you know the speed of light is always a constant, so you can always calculate the wavelength, and so on. So it's really useful. These equations are really, really useful. If you're not taking calculus, then I hope you were able to follow at least a little bit of what we were doing, but this is the holy grail result that you're trying to achieve. This is really the point, and if you're not taking calculus, then in all likelihood, your book probably didn't even do this, and it just said this is the velocity of a wave. That's okay. If you're taking calculus, I hope you understood that all we were doing was taking the argument, holding it constant, that was allowing our point to move from A to B, we talked about that. Take the derivative of both sides and solve for dx dt, which is equal to the velocity. By definition, dx dt is the velocity of a wave. All right. One more quick thing, and then we'll jump into some problems. I want to talk to you about the direction of wave travel. Direction of wave travel. Now, we already talked a great deal about y as a function of x and t is equal to ym, which is the maximum amplitude, times the sine of kx minus omega t. And we already talked about, well, actually, we haven't talked about this yet, so let me back up and slow down a little bit. This is what we've talked about as a traveling wave. The bottom line is, if there's a minus sign here, if there's a minus sign, then the wave travels in plus x direction. In other words, it goes this way. The wave travels this way, right? That's what that means. If you have an equation of a wave that looks like this, amplitude times the sine of kx plus omega t, the only difference between them being that this is a plus, then this wave travels in the negative x direction, which just means it's traveling this way. That's very much opposite of what you might think, but you need to memorize that. Basically, you're always going to look at these things with a minus here. Kx minus omega t, kx minus omega t. That always means it's traveling to the right, like you would think. If you ever see a plus, or if you have to write an equation of a wave that's going the opposite way, you have to put a plus there, or otherwise it's not the correct wave. If you need a quick and dirty way to remember that, if you remember from Algebra 1, if you were going to shift a function to the right, like sine, let's say, if you were going to shift it to the right, you always subtracted a number, right? X minus 3, let's say. It means you're shifting the sign to the right. If you were going to shift it more to the right, you would subtract more. If you were going to shift it even more, you would subtract it even more. Well, you see what's happening here as time goes on, the reason the wave propagates, saving the grand finale for last, one way to think about this wave propagating is that as time increases, this whole thing increases. As time goes up, this little part increases. So as each second elapses, I'm subtracting bigger and bigger and bigger number, which causes the wave, the entire sinusoidal shape, to shift to the right more and more and more as time goes on. That's how the wave propagates. Same thing from Algebra 1. If you had x squared was your function, and you were going to shift it to the left, it would be something like x minus or x plus 3 squared. When you have a plus, it's shifting it to the left. If I wanted to shift it more to the left, it would be x plus 100 squared. The bigger number I put in here, the more it's shifted to the left. So the same thing here. I have a plus, and as time goes on, I'm shifting it more and more and more to the left, so the entire wave is traveling to the left. So basically, this is telling you when you have a minus, your wave is going that way. When you have a plus, the wave is going the opposite way. So that's very, very important for you to remember. And I actually lied. I have one more little thing to share with you before we call it a day here. The wave, let's talk about briefly the wave on a stretched string. Now, everything that we've talked about up till now is completely applicable. This equation of a wave, the speed of a wave, all that stuff is exactly right. But people have devised, special equations that apply when you have a string, a rigid string that's stretched. Notice that as I pull the string, it has a certain tension in the string, and of course I can send waves down there. I can send waves down to the end of the string, but I have a tension in the string, and the string has a certain weight to it. In other words, it's got mass. And so the velocity of the wave in a string, it turns out, is very much related to those things. Now, all of this stuff applies, but it turns out in a string, it's worth it to go ahead and define the velocity of a wave a little bit easier that you can measure in the lab. It's the square root of the tension in the string, which I'm going to label with a funny t that looks like a t like that. It's called tau, divided by mu, which is basically the mass of the string, the mass density of the string. So let's go ahead and talk about what these are. T, which is tau actually, is just simply the tension in string. In other words, tension in string. In other words, how tight is it? How many newtons in tension are you actually holding here? And mu is what we call the linear mass density. And I think you'll understand that when I show you the units. That would be, mu would be units of kilograms per meter. In other words, mass per unit length. Mass per length. In other words, that jump rope has a certain mass for every foot or every meter that I go, and of course that's going to affect how the thing propagates. I'm not going to prove it to you. Most books don't prove this to you, but if you were to take the tension in the string and divide it by the mass density, which basically tells you how heavy that string is, then you do this in kilograms per meter and you do this in newtons, let me put that in parentheses here, you're doing this in newtons, then what you're going to get is meters per second. I'm not going to derive it for you. I'm not going to make it more warm and fuzzy for you. So I'm not going to prove it, but you can kind of see, I do want to point out that if you increase the tension in the string, then the velocity does increase. And if you decrease the mass density, which is basically decreasing the mass of that string, then the velocity increases. So what I'm trying to say here is, so for a fast wave, you want a light, tight string. In other words, to get a very fast speed out of the wave, you want a very lightweight, very tight, taut string. It kind of makes sense. If you have a really heavy 100-ton chain, right, you're not going to have a very fast wave because that thing's going to be so heavy it's not going to be able to propagate on down the way. And so what you want is you want a very tight, and you can kind of see this here, you want a very tight string. You can see, I mean, the waves are really, I mean, you can't even see them go up and down very easily, but they're really traveling very fast to the end. Whereas if I have very loosey-goosey, not very much tension, the wave is slower. It makes it to the other end, but it's slower. So this is nothing really phenomenally different than what we've talked about before. This is an equation that applies only to strings, okay? The F lambda still applies, everything else still applies. It's just that when you're in the lab, it's really easy to measure the tension in a string. It's very easily to weigh a string or to calculate the mass of a string, so you can find out what these are. And people have derived that when you do this division, take the square root, you get meters per second. Okay, so this was a lengthy section. We've covered a tremendous amount of material. We're going to stop it here. Next section we'll have all of our problems. We have quite a few problems to get this home to really give you practice with understanding waves. Just remember, there are two kinds of waves. You have your longitudinal waves, which are your sound waves, and the medium is oscillating back and forth in the direction of propagation. That's not what we've really talked about too much in this section here. We've talked more about transverse waves, which means that you have an oscillation perpendicular to the direction of motion off like that. That would cover your water waves, your string waves, and your electromagnetic light waves as well. So we talked about the definition, the mathematical definition of a wave. We've talked about the wave number, the angular frequency, the amplitude, which direction, left or right, the wave is propagating, the speed of the wave. You have all of that in your head to understand what waves are about. Now let's go ahead to the next section and solve some real problems. I'm Jason. I hope you've enjoyed this section. Let's go off to the next one and work some real problems.
Learn anything at mathandscience.com.